Okay, so this is chapter 5. It should say section 4 here, so that's actually a typo. And we're going to be talking about the sum and difference formula, so let's take a look. Alright, when we're talking about the sum and difference formulas, we're talking about this set. When I'm memorizing these formulas, this is how I like to personally memorize it. I memorize sine. I don't care if it's the sum or the difference. So I'm looking over here. I don't care if it's the sum or difference. Notice that the pattern for these two things are the same. It's sine of the first angle, cosine of the second angle, cosine of the first angle, sine of the second angle. If it's addition here, then I'm adding two angles together. Then the formula, I'm going to be adding the components together as well. Over here, when I have the difference, it's the difference. For cosine, notice that the pattern is cosine, cosine, sine, sine, and it didn't matter which one I was looking at. So cosine of the first angle, cosine of the second angle, either plus minus, sine of the first angle, sine of the second angle. If you're adding, notice that the sign switches. If you're subtracting here, notice that the sign switches as well. So for sine, the signs stay the same. For cosine, the signs are switching in these formulas. For tangent, let's take a look at tangent when we're memorizing these. Notice that the numerator, the sign is consistent. The denominator, that's where the sign is reversed. So if I'm subtracting the numerator, I should be subtracting. In the denominator, flip it over. So let's explore tangent. When we're finding the tangent sum or difference of two angles, we're doing the tangent of the first angle, either plus minus the tangent of the second angle. In the denominator, it's always 1 minus or 1 plus the product of tan of first angle, tan of second angle. So what am I talking about? Well, this is what I'm talking about. Let's say we have, I'm going to make up an angle right now, 15 degrees. Let's say I want to evaluate, I meant to write, yeah, that's fine, cosine 15 degrees. Well, can I use the unit circle to evaluate cosine of 15 degrees and find my exact value? No, but I can manipulate angles on the unit circle so that I get 15 degrees. Can I think of anything on the unit circle that I can either add or subtract to get 15 degrees? Good, 45 and 30. So if I can rewrite this as cosine of 45 degrees minus 30 degrees, and that gives me 15 degrees. So I can find the exact value of cosine 15 degrees using the unit circle now. So the formula says for cosine, and if it's the difference, that means I'm going to be adding. I take cosine of the first angle, cosine of the second angle. The signs switch for cosine, so it's plus the sine of the first angle times the sine of the second angle. I wrote 45 twice. I meant to write 15 over here, by the way. Cosine, I meant to write sine there. Sine 15 degrees. So notice that I just substituted the first angle and the second angle into the formula. So now okay, I meant to write 30 degrees. 15 degrees was the given. So this should be 30 degrees. And this should be 30 degrees. Okay, so now I can use my unit circle to evaluate cosine at 45, 30, sine at 45, and sine at 30. Well, cosine of 45 degrees, that's root 2 over 2. Cosine at 30 degrees, that's root 3 over 2. Sine at 45 degrees is root 2 over 2. And sine at, that says times, at 30 degrees is a half. So now I'm going to find the product of these two and add them. What do I end up with? I end up with root 6 plus root 2 over 4. And that's the exact value for cosine at 15 degrees. So that's exactly what we're going to do. We're going to manipulate angles so that we can use the unit circle to find the exact value using the sum and the difference formulas. All right, so now let's take a look at our first example. It says find the exact value of each expression. And this problem was very, very nice. They broke up the angle for us, okay, so that now I just have to substitute it straight into the formula. So let's go ahead and do that. So if I'm doing the cosine, the sum of two angles, the formula says it's cosine of the first angle, cosine of the second angle. Remember, cosines, the sign is going to switch in the formula. So from plus, I'm going to go to minus. Sine of the first, sine of the second. Okay, so now we're looking at the unit circle and we're determining cosine at 120 degrees. That's negative a half. Cosine at 45 degrees is root 2 over 2. Sine at 120 degrees is root 3 over 2. And sine at 45 degrees is root 2 over 2. So our answer ends up being negative root 2 minus root 6 over 4. All right, let's do the same thing here on B. Here I have the sine. So when I have sine and I'm going to set it up, the formula is the sine stays the same in the formula. For sine, it stays the same. So sine of the first angle, cosine of the second angle, minus cosine of the first angle, sine of the second angle. And now I'm just going to simplify that using the unit circle. Okay, so let's go ahead and do that. At 7 pi over 3, well, I know that has to be over 2 pi. Why? Because 6 pi over 3 would be 2 pi, right? 6 divided by 3 is 2. So I went over pi over 3. So really 7 pi over 3 is at pi over 3, just one rotation around the unit circle in addition to pi over 3. So when I'm evaluating sine at 7 pi over 3, I'm really evaluating sine at pi over 3, and that's going to be root 3 over 2. And then cosine at pi over 3 is a half, minus cosine at 7 pi over 3, a half. And then sine at pi over 3, that's root 3 over 2. So when I simplify this, I end up with root 3 over 4 minus root 3 over 4. What do I get? 0. So the exact value for that was 0. All right, here this example is a little bit different. What's different about this example is that you actually have to come up with either sums or differences in order to use those sum and difference formulas. You can, and take a look, we're actually evaluating the exact value for sine, cosine, and tangent by either using a sum or a difference. So it doesn't matter what I pick, so let's think of 105 degrees. All right, well, what angles can I sum from the unit circle to get 105 degrees? So we just came up with 3 different ones. Does it matter which one we use? No. I can do 135 minus 30. I could do 150 minus 45. I could do 60 plus 45. As long as I'm using values from the unit circle so I can evaluate it using the unit circle, then we're good to go. I'm going to pick an easy one. I'm going to pick 60 plus 45. So let's just pick 60 plus 45 degrees. So that way we can stay in quadrant 1. And then it's easy to remember what's sine, cosine of 60 or 45 degrees. So let's start with cosine, the sum of 60 and 45. So remember, when we're doing cosine, the sign is going to switch. So if I'm starting with the sum of 2 angles in the formula, I'm going to subtract. So cosine of the first, cosine of the second, minus sine of the first angle, and then the sine of the second angle. So what's cosine at 60 degrees? The radian equivalent is pi over 3, by the way. Half. Cosine at 45 degrees is? Good, root 2 over 2. Sine at 60 degrees is? And sine at 45 degrees, root 2 over 2. So now I can simplify this. I end up with root 2 minus root 6 over 4. That does not reduce any further, so that's our solution. All right, so now let's evaluate the sine of the sum of these 2 angles. So we're going to do the sine of the first angle, cosine of the second angle. Remember, the signs for sine stay the same. So plus cosine of the first, sine of the second. And now I'm just going to use my unit circle to substitute. So at sine of 60, we already evaluated that. We said that that was root 3 over 2. Cosine at 45 degrees, that's root 2 over 2. Cosine at 60, that's a half. And sine at 45, root 2 over 2. So here we end up with root 6 plus root 2 over 4. That's a 2. It doesn't really look like one, but it is. All right, so let's evaluate the tangent of 60 plus 45 degrees. So yes, we're going to take the sum. Remember the numerator, the signs stay the same for tangent. And the denominator, that's where you do one opposite sign of the numerator. So if we were adding, then we're subtracting down at the bottom. And then it's the product of these two measurements. Okay, so tangent of 60 degrees at pi over 3, you're going to put root 3 over 2 over a half. You end up with root 3 minus tangent at 45 degrees is 1 over 1 minus, and then we have root 3 times 1, which is root 3. Okay, so from here, so we have root 3 plus 1 over 1 minus root 3. I accidentally didn't bring that over here. So you cannot leave a radical in the denominator. You need to do what? Good. Multiply it by the conjugate pair, which is going to be 1 plus root 3. And remember, the thing about conjugate pairs is that when you're multiplying by them, you just need to multiply the first and the last term. Because they're conjugate pairs, the middle terms will reduce. In the top, we have to FOIL all the way through. First term, we get root 3. Second term, I get plus 3. Third term, I get plus 1. And then I get plus radical 3. When we combine like terms in the numerator, in standard form, you get, if your first number is, you actually have the sum of 3 and 1, which is 4, and then you combine your radical term. I have plus 2 root 3 over negative 2. Because everything is divisible by 2, that's when we can divide. So 2 goes in there once, in there 2 times, in there once. So our solution is, and remember I have a negative in the denominator, so that means my numerator signs are going to switch. So it's minus 2 minus root 3. All right, I'm not going to do B because then it's just going to be repetitive. Again, you're just substituting the angles. What you need to know is which angle measurements from the unit circle can you actually substitute into the actual formulas for sine, cosine, and tangent, the sum and difference formulas of those. Well, here are some options from the unit circle for 285 degrees, and it does not matter which ones I pick. I'm going to end up with the same solution. So what we're doing in this example is we want to write it as a single angle. So now we're taking those formulas from the right side and we're going to the left. We're going to condense it. We need to identify which formula was being used. All right, so now I want to actually condense it. So I need to think what formula was used. Well, if you look over here, cosine, cosine, sine, sine, I know that that must be cosine. And remember, cosine has opposite signs for the formulas. So what I want to do is I'm going to actually add these angles. And I end up with cosine of 40 degrees. That's definitely not from the unit circle, but that's not what this question's asking us. It didn't say evaluate or find the exact value of. It just said to express using a single angle. And I just did that. I brought it using the left side of the formula. I'm going to do the same thing down here. If I see tangent, what formula was used? Tangent. If I see plus at the top, that means I'm adding the angles together. And my answer here is tan of 3x. And the exact value of a single angle. So we're going to do what we just did in the previous example. We're going to condense it, but this time I'm actually going to evaluate. Let's take a look at example 4. It says find the exact value of the expression. So exactly what we're doing in example 3. I'm going to condense it. I need to identify which sum formula or difference formula is being used here. Well, if I have sine, cosine, cosine, sine, that must be the sine formula. And remember, in sine, the signs stay the same. So that means I'm going to be subtracting these angles. So 330 minus 30 is the sine of 300 degrees. Has a reference angle of 60 degrees. At 60 degrees, sine is what? So that is going to be root 3 over 2. However, because we're in quadrant 4, I know I have a negative solution. So that's how we use reference angles to help us out. So my answer is negative root 3 over 2. If I'm looking at example B, I know tangent's being used here, tan, and if sum is in the top, that means I'm going to add those angles together, and I get the tangent of 135 degrees. That reference angle is 45 degrees, tangent at 45 degrees is 1. But in quadrant 2, because that's where 135 degrees lies in, right? Tangent is negative. So my answer is -1. Okay, so this example is a little bit different. Suppose that cosine of theta is equal to -3/5 for a quadrant 2 angle. And cosine beta is equal to 12/13 for quadrant 1 angle. Find the exact value of each of the following. Well, in order to find sine for theta or beta, I need to draw triangles. So for these type of problems, it's imperative that we draw triangles. So let's begin by drawing our quadrant 2 triangle, which was theta. So I'm going to put, remember, theta always comes out from the origin. We're going to put our triangle in quadrant 2. Tells us that cosine is -3/5. Using our Pythagorean triples, I know that this side must be 4. So sine of theta, remember SOHCAHTOA, TOA, opposite is 4, hypotenuse is 5. So now I have cosine, which was given to me, by the way, of theta, and sine of theta. Now I want to do the same thing in order to have sine and cosine of beta. And in the problem, it tells us that beta is in quadrant 1, so I'm going to draw a quadrant 1 triangle. So let's put beta there. And we're told that beta is 12/13 for cosine. So if we're looking for the opposite side, using our Pythagorean theorem, we get 5. So now we have cosine of beta, which is 12/13, because that was given to us. And we have the sine of beta, which is 5/13. Okay, so we did all this to find the sum of theta plus beta. Okay, well, before I do that, I want to go ahead and actually set up the formula first. Make sure you do that so you don't accidentally substitute something incorrectly into the formula. Well, the sine is, remember, sine, cosine, sine of the first, cosine of the second, the signs stay the same, cosine of the first angle, and then sine of the second angle. So now I can do direct substitution. So I'm literally going to say, what's sine of theta? Well, this is sine of theta. So directly substitute it. So sine of theta is 4/5. Cosine of beta, oh, I wrote that backwards, didn't I? This is supposed to be, just realized I had a typo. This is supposed to be cosine. So now substitute that. That's going to be 12/13 plus cosine of theta, that's up here, -3/5. And sine of beta, that's right here. That's what we solved for, 5/13. So now that I have that, I can simplify the fractions. So 4 times 12 is 48 over 65 minus 15/65 gives me a sum of 33/65. All right, so for part B, when I'm doing cosine of theta plus beta, again, make sure that you rewrite this using these given angles, so that way you don't accidentally substitute something that shouldn't be there. So cosine of theta, it's -3/5. Cosine of beta, that's 12/13, minus sine of theta, which is 4/5, and sine of beta is 5/13. Now let's simplify what we have here in the denominators. We are going to have 65 because that's what we had at the top. Then I'm going to have minus 36 minus 20 equals -56/65, and that's already simplified. Now we want to actually prove the identity using our sum or difference formula. So this is going back to lesson 5.1 for the proofs. So what I'm going to do is I'm going to work on the left side, and I'm going to introduce the difference formula for sine. So it's sine of the first angle, cosine of the second angle. Remember, the signs for sine stay the same. Cosine of the first angle, sine of the second. Now I can actually use concepts from the unit circle. At pi over 2, I know the coordinate point on my unit circle is 0, 1. Sine, therefore, is 1. And then we're going to have times cosine of x. And cosine is going to be 0 times sine of x. Anything times 0 is 0, and anything times 1 is itself. So this proof was relatively easy because it was just a matter of simplifying using the difference formula. And notice that that's what we got. Alright, so here's example number 7. It says find all solutions of the equations on the interval from 0 to 2 pi. And we're not including 2 pi. So what we're going to do is we're going to treat this like our previous lesson. First, I'm going to start by breaking up that first part using the sum formula. And this is going to be sine of x, cosine of pi, plus cosine of x, sine of pi, minus sine x. I'm going to swing that 1 to the other side. We can evaluate this term and this term using the unit circle. At pi, the coordinate point is -1, 0. So remember, x is cosine. So here I can substitute -1, and sine is the y term. So when I rewrite this, I get minus sine x equals -1, because 0 times cosine, this term is gone, and this becomes negative sine x. Make sure we combine like terms. I get minus 2 sine x equals -1. Sine x equals 1 over 2. And now this brings us back to yesterday's concept. Where is sine of x equal to 1/2? So our solutions on the interval from 0 to 2 pi, x equals pi over 6, and x equals 5 pi over 6.